This interesting little thing is a flame detector tube. It has no moving parts, it doesn't wear out, and can detect even small flames from several meters away. Not only are these things highly sensitive to fire and flames of almost any kind, but they are also totally immune to the effects of sunlight and other lighting. Within this small, curious glass envelope, there appears to be almost nothing of significance. It just appears to be a metal plate with something resembling a paperclip on one side of it. So, how can something so simple behave as a highly sensitive detector of fire? Well, today, we are going to figure out what this interesting sensor does, and more importantly how it actually works. Every project has an origin story, but in this case it is pretty simple. One day, my human assistant was browsing the Chinese equivalent of Amazon, called Taobao, and he found this odd little thing. Neither of us had ever heard of these things before, or had any idea how they worked, so we resolved to do something about that. What we found was that the available information on this type of flame detector is pretty sparse. The manufacturers of these tubes are pretty coy about disclosing too many details, and even Wikipedia has very little to offer on this subject. So, there was nothing for it, we were just going to have to run some experiments, to see if we can figure out some of the missing details for ourselves. In this case, it did mean that we were going to have to buy quite a lot of equipment to run those experiments. In fact, we did end up completely blowing out our budget on this project. But, it's all for a good cause, and we will have some very useful equipment for our future projects. So, we threw caution to the wind and went on a jolly old spending spree. Right, let's go and figure out how this thing works. This is a very simply constructed little tube that consists of little more than an anode, a cathode, a glass enclosure and a gas filling. Yet, as you will see later, it has an incredible level of sensitivity and a blindingly fast response time. Looking through the datasheets for these types of devices, we did get some hints. Firstly, this is actually an ultraviolet detector. This might seem counterintuitive at first, after all, fire is hot, so we might expect that the thermal wavelengths would be a better place to be looking, when trying to detect flames. But, the issue with the thermal wavelengths, is that our environment is filled with lots of sources of thermal energy that could confuse a flame detector, including people just walking around. So, if we want to detect flames, what is needed is a part of the spectrum that typical flames will produce, but our everyday life does not. First, let's look at the fire itself. This typically behaves as a black body radiation emitter, and has a characteristic curve. And, we have to find a part of the spectrum that won't be affected by sunlight. Fortunately, we have an atmosphere that blocks some of the most dangerous parts of the ultraviolet spectrum. In this case, everything below 300 nanometers is blocked. And, this is the region where these UV flame detector tubes are sensitive. The black body emission of a typical flame has a curve that almost falls to zero in these wavelengths, but almost is not zero, so some energy still remains in these UVB and UVC bands. So, when these ultraviolet photons strike the cathode, if they have enough energy, they can dislodge an electron. This now free electron then shoots out of the cathode, striking the gas molecules in the tube, causing them to also release electrons. Eventually, this builds up into a cascade of negatively charged electrons, rushing to the positively charged anode that they are attracted to. In order to make this happen, the applied voltage must be very carefully controlled to be within some pretty narrow limits. too low, and an electron cascade will not start, too high and it won't stop. There is a very small amount of a quenching gas within the tube, this is usually chlorine or bromine, and helps to prevent the cascade from continuing indefinitely. This whole mechanism has a lot in common with Geiger-Müller tubes that are used to detect radiation. We will be performing some experiments on that aspect later. We also noticed that in the data sheets that many of the tube types used nickel for the cathode, but others used molybdenum. It was also noted that the ones that used the nickel cathode were stated as being immune to sunlight, but the ones with the molybdenum cathode did not have this feature. Now, if we look up the photoelectric work function for both of these metals, and then convert those energies to wavelength, we can see why the type with the molybdenum cathode has a wider stated spectral range. It is just easier to knock the electrons out of that material than it is for nickel, and the numbers seem to match pretty well. We bought some second-hand spectrometers on the Chinese equivalent of eBay, called Shenyu. One is a visible and IR spectrometer and the other is an ultraviolet type. Best of all, we got the lot for about $225. Sadly, our little garden spectrometer can't help us with working in the ultraviolet regions of the spectrum. So, now we know the basic theory of this flame detector, it's time to do some experiments to show what it can actually do. We bought this little board to drive the tube and allow us to quickly get some experiments done. As you will see later, this PCB did have some limitations. Let's start by seeing how far it can detect the flame from a cigarette lighter. Here the tube is 1 meter away from the flame. This was clearly an easy test for this little detector tube, so let's move it further away and try again. Now, if we test this from 2 meters away, once again the response is basically instantaneous. Well, I guess we should keep going. It's just a little glass tube after all, I mean how sensitive can it actually be? Oh. Right, let's push it right to the end of the room then. Okay, so now it's at the limits of the room, which is a distance of 4 meters. And, again we get an instant reaction to this flame being ignited. So, we figured we would try some other sources of fire, and see if we get a similar reaction. This time, we are going to first light a candle, cover it, then switch on the flame detector. When we uncover the candle flame, at a distance of 4 meters, the flame detector is almost instantly triggered. So, let's use our new ultraviolet spectrometer to look at this candle flame and see if this does in fact have any UVB or UVC components. While the level is quite small, there is indeed some amount of the optical energy in this band, and clearly it is enough to be detectable. So far so good. Let's try something else, like a match. Once again, we are going to be testing this from a distance of 4 meters. It seems that this little flame detector tube is pretty bloody sensitive. So, is it really possible that the light from a match can contain enough ultraviolet light to trigger this tube? Let's take a look with the spectrometer. Once again, we can see that a continuous spectrum, that we see from an almost ideal black body source, will give enough ultraviolet in the UV band to trigger this device. Right, let's try using an alcohol fire, these are supposed to burn with an almost colorless flame. In our case, it seems like the wick is burning to carbon and becoming incandescent. Immediately, the flame detector tube reacts. So much for sources of fire, let's move on, and try some artificial sources of light, and see if those are also able to trigger this flame detector tube. Given that we know that this tube is actually detecting ultraviolet light, in the UVB and UVC wavelengths, we thought we would test this using some ultraviolet flashlights. We think that these flashlights are producing light which is UVA, so this detector should not respond to these. And using our flashy new ultraviolet spectrometer, we are able to confirm that there is no UVB or UVC energy being emitted from these LED flashlights. So, let's get on and see if our flame detector can be confused by strong UVA lighting sources. As you can see, none of the UV flashlights that we own are capable of triggering this little detector tube. That is a pretty interesting result. This is a mercury arc lamp, and we know that it can produce some UVC light, as it is used for sterilization purposes. Although this should not be viewed without appropriate safety goggles, the visible light that this lamp emits is very beautiful. So, let's use the UV spectrometer again to see what light this thing is emitting. If we compare with a reference spectrum, we can see that both the wavelengths and relative amplitudes are pretty close to the values we are capturing. So, the moment of truth. Yes, almost instantaneously, this lamp will trigger the flame detector tube. This interesting thing is a deuterium arc lamp, which contains heavy hydrogen. It is a very specialist lamp that is used in spectroscopy applications, and produces a continuous ultraviolet spectrum. Although the visible light from this lamp is a little dim, you can see in the spectral plot that this thing is emitting a great deal of short wavelength ultraviolet energy. Eye protection is vital when using this tube. There really wasn't any question about this light source being able to trigger this detector. But it was a good excuse to show everyone our favorite lamp. This is a halogen lamp. It is basically an incandescent lamp, with some clever chemistry added, that means it can run hotter, and so it can produce a more white light. More white means more blue, and thus potentially some ultraviolet light as well. And indeed, there is a very small amount of UVB and UVC, so let's see if it is enough to trigger this flame detector. Oh dear. Looks like halogen lighting will create false triggers for this type of UV flame detector. Let's try a regular old incandescent bulb. When we analyze this light, using our UV spectrometer, we still see a very small component of ultraviolet in the continuous spectrum of this lamp. So, let's find out if this can trigger the flame detector tube. Well, despite having a small amount of ultraviolet, it seems it is not enough to trigger this detector. Let's try some other light sources. This is a red laser with a power output of about 60 milliwatts. Although this might not seem like a very powerful laser, because it is collimated, the energy density at the spot is very high. Let's see how this detector tube reacts to this laser. Well, this red laser appears to have no effect, and does not cause a detection event. So, let's try using a shorter wavelength, such as this green laser. It has a wavelength of 532 nanometers, and an output power of about 50 milliwatts. Again, the detector tube gives absolutely no response. This is a violet laser, that has a wavelength that almost reaches the ultraviolet, about 410 nanometers, and a power output of 60 milliwatts. Now, this time, we get a reaction. The flame detector triggers almost immediately. Later, we will talk about why that is possible. From the datasheet for this tube, we learned that the tube can also detect sparks. So we decided to test that. As you can see, we get a fast reaction. So this thing can clearly detect sparks. And then, We wondered what the spectrum of these sparks looked like and decided to take a look into that. First of all, we tried to make an enclosed box, to try and detect the faint light that was emitted from our weak sparks. But that didn't work, so we came up with a new idea. We would use a microscope slide to keep everything in place. And this worked really well, except the electromagnetic emissions from the sparks kept crashing the spectrometer. So, we changed to a 5-meter optical fiber, which allowed the spectrometer to be kept well away from the sparks. And finally we managed to capture that spectrum we wanted. I'm not really sure what we were expecting, because the results were pretty obvious once we got them. Basically, this is just the ionization spectrum of the nitrogen from the air. And once we compared with a reference spectrum, we were able to confirm that. Here, you can see the UV peaks that are triggering the flame detector. So, about that claim, that these things are immune to sunlight, we really ought to test that. And then we hit an issue with the cheap PCB that we bought. We have been seeing issues throughout our experiments. Later, we checked the high voltage and found that it was bouncing around all over the place. So, we bought a new one. A much better one, and now, we can trigger it with a cigarette lighter, but it doesn't react to the sunlight. It also just shows the raw detection events, and doesn't latch in the triggered state. That will be useful for another experiment later. So now, let's capture a spectrum of the sunlight that is striking the ground. We should be able to see why this tube isn't triggered by sunlight. Immediately, we can see that there is basically zero ultraviolet content in the sunlight below 300 nanometers. This has been filtered out by the Earth's atmosphere. To be fair, if the atmosphere didn't have this property, then you humans would all be fried to a crisp. And despite being in sunshine, this interesting little sensor is still able to detect fire. Whilst looking through the datasheet for this device, we noticed something. In many ways, this device has a lot in common with a Geiger-Müller tube. Given that we have a few radioactive test sources available, it would be a shame to not test with those. This is a small sample of americium-241. It decays mostly with the release of an alpha particle, but those cannot penetrate the glass of this tube. What is giving those occasional detection events is the weak gamma emissions from this test source. This is a sample of cesium-137, which is normally a very scary substance. This test source only contains slightly less than 1 microcurie of this isotope, yet the flame detector tube is still able to occasionally detect the gamma emissions from the source. This is the pointer hand from an old Soviet military compass, and it contains some radium-226. This flame detector has no trouble picking up the emissions from this radioactive isotope. And now it's time for the crowd pleaser, strontium-90. This is a fairly strong beta emitter, and the little flame detector gives a very clear response to the presence of this test source. While none of these reactions are of the kind of sensitivity one would expect with a real Geiger-Müller tube, these flame detectors are able to detect gamma and beta radiation. This is a soft X-ray source, and we are going to use it to see if this tube can also detect these low-energy X-rays. And clearly it can. Even these 10 keV X-ray photons can be easily detected. And finally, we wanted to know what gases are present in the flame detector tube. None of the manufacturers supplied any data on this. We asked the major artificial intelligence tools, and those came back with non-specific bullshit answers. Right, as usual, we are just going to have to find out for ourselves. So here is the plan. We are going to ionize the gas within the tube, using a high voltage generator, and then use our visible light spectrometer, to try and measure any characteristic lines that may be present. We actually bought 2 tubes that have the same part number, one is a generic type, and the other is made by Hamamatsu. And they actually appear to have slightly different gas mixtures. We are not able to detect the quenching gases. These are normally used in extremely low quantities compared to the main gas filling. Both tubes appear to use neon gas as their main gas filling, but the Hamamatsu tube also appears to have some argon included in their gas mix. I guess that the exact tube gas mixture is each manufacturer's trade secret. These new spectrometers are rather splendid, but I can't help but think that maybe we have forgotten something, or someone. One big advantage that this new board has, is the speed of response. And this allows us to perform an experiment, to find out exactly how quickly this little flame detector can respond. We have seen that the response is pretty fast, so we will try and discover the minimum detectable duration of exposure to UV light, that will trigger this thing. We are going to use an ultraviolet LED, as the source of the UV. So, we mounted it to a little board, and added a heatsink. You can see that when it is turned on, the lens from this magnifying glass will fluoresce, so there is certainly some UV present. This LED claims to emit 254 nanometer ultraviolet, which makes it a UVC LED. So we decided to test that claim with our spectrometer. And we were pleasantly surprised to see a nice peak at 254 nanometers, just as the vendor had promised. There are just so many traders out there that missell UV LEDs. We did this experiment in our office, which allows us to test another light source, fluorescent lighting. When we disable the 50 Hz video masking from this video, you can clearly see the lights flashing. Right, let's run this experiment. Here you can see that the tube clearly is responding to a 500 milliseconds UV pulse, every second, so running at 50% duty cycle. Now we have reduced the pulse width to just 100 milliseconds, and this tube reliably responds to each pulse. At 50 milliseconds, it still continues to operate correctly. So, let's crank up the speed. We are now at 10 milliseconds, and still everything looks good, which I am sure you will agree, is pretty impressive. We are now at 2 milliseconds, and still this little flame detector tube is taking everything in its stride. Incredibly, using 1 millisecond pulses, we are still able to trigger this tube. Now, once we reach 500 microsecond pulse length, the system seems to occasionally miss some pulses, so we are reaching the limits of the performance of this tube, and of the circuit. But, even when we are only firing 100 microsecond bursts of UV light, this little tube still responds to most of the pulses. Frankly, that is bloody amazing. I don't think that there is any other fire detection technology that is able to respond so quickly. Well, that's it for the experiments. I can't help but think that there is one more thing I have forgotten to mention. If you have been wondering what all of those references are to something called the Little Garden Spectrometer, then you might want to skip ahead to the next chapter. If you are one of those 2,000 plus people that bought it, or are just interested in low-cost spectrometers, then please watch on. Today, we are going to meet Mr. Kang in person. Spending time using those high-end spectrometers made us feel that somehow we were disrespecting our friend, Mr. Kang, the creator of the Little Garden Spectrometer. So we decided to pay him a visit. Hello, Mr. Kang. It is my honor to finally meet you.
你好，奥桑， 很高兴认识你，欢迎来北京。
So, we are here in Beijing, and have come here to ask you about what new things you might be working on. Many of our viewers were highly appreciative of the efforts that you have put into the little garden spectrometer. So, please tell us, what's next?
我现在正在做，一个设备呢，是打算做拉曼光谱仪，但是现在还没有做好呢，等过段时间就好了。
Wow! Raman spectroscopy is something we have a great deal of interest in learning more about. Would really like to know how you remove that Bayer filter. Perhaps you can tell us about that.
不行，对不起，目前还不行，这是我的一个秘密。
So, Mr. Kang, how about a little drink? Now, about that secret process.
这个去贝尔阵列。
Of course, we were never going to trick our friend. But, the plum wine was bloody good booze. When we first saw this funky little tube on Taobao, we really had no idea what it was used for, let alone have any idea how it worked. Later, we discovered that these things are in common use, albeit in industrial applications. The tube themselves do not appear to be terribly expensive, we paid about $12 for them each. On the whole, these are used in professional fire detection systems, and are frequently seen in industries like oil and gas, power generation, shipping, chemical and heavy engineering. So don't expect to find these in Home Depot. We would just like to circle back to a couple of points raised in the experiments. The halogen lamp was able to trigger the flame detector, but this is not a common and garden type, this one is intended for spectroscopy applications. The types that used to be intended for domestic usage, typically include an ultraviolet filter, which removes this dangerous part of the spectrum. To be fair, it's pretty hard to buy any incandescent bulbs these days. So, let's just take a look what happens when we test one that is intended for domestic use. We don't get any triggering, and this one is a 35-watt type, with a reflector, far more powerful than the type we originally tested. Now, let's just look at that other curious result, when the flame detector was triggered by the violet laser. The issue here is not just about wavelength, it is also about the optical energy density. This is the spectral response for the flame detector tube, and is taken from the datasheet. You will notice that at wavelengths outside of its spectral range of operation, the response is not specified. That response curve doesn't just fall to zero outside the specified range, it asymptotically approaches zero, but never quite reaches it. So, if you apply enough optical energy at 300 nanometers, then this tube will trigger. And, the same is true at the wavelength of the violet laser. We can conduct a quick experiment to demonstrate the power density that this 60 milliwatt laser can deliver. We are going to use that 35-watt halogen lamp again to illuminate a black piece of card. This level of illumination is far higher than even direct sunlight, and the heating that the card undergoes is clear in the thermal camera image. But, even with this level of background illumination, the energy delivered by the violet laser is clearly visible. This little laser might not have a lot of total power output, but all of the power it produces is all delivered to an extremely small area. Well, at least that is our best explanation for this. If you have a better one, please feel free to let us know in the comments. These little ultraviolet flame detector tubes are far more interesting than we initially gave them credit for. And it does have to be said, they do have the simple beauty of the age of the thermionic vacuum tube. And yet, these are modern devices that have modern applications. Our only regret with this project is that we didn't buy more types of this tube to test. Because of their similarity to Geiger-Müller tubes, this is a great crossover project between our usual subjects of nuclear physics and optics. We are working on a few different projects right now, but if you have any suggestions, please do feel free to let us know your ideas in the comments. Good ideas are welcome, bad ideas will be tolerated. The only truly terrible thing is to have no ideas at all. And finally, please don't forget to give this video a thumbs up. Anyway, that's all we have for you today. We hope you enjoyed our little video, or at least found some parts of it interesting. If you think we deserve it, then please feel free to give it a like. And you could always hit subscribe if you want to see more content like this. This channel doesn't have any sponsors, nor are we looking for any either. But, if you like what we do, and have far more money than you know what to do with, you could always consider dropping us a small super chat. We do hope that you managed to learn at least one new thing in this video, and that your investment in time was rewarded. Time is the only truly valuable resource we have. This is still a hobby channel, so we can say what we want, and YouTube's algorithm can go and get f***ed. Thank you for your time. You now have only a very short time to choose the next video to watch.
3, 2, 1.